So great. Now it's 4:35. So thank you all for coming. Today I'll be talking about this topic. Hopefully it's a topic you guys are all interested in, which is toward PhD, how to do research. So for those who, I think most of people here know who I am. So I'm Shih-Hao. I'm currently a postdoc at John's group. So this talk is intended for our group people, so it will be much more oriented to theory-based research. But I hope the things we discuss today will also apply to whatever other research you guys are doing. So let's start. I would like to start with this question. So what is a PhD? Because lots of students ask me how to do research. But I think there's a much more important problem. So before we try to know how to do research, let's see what research degree really means, right? What is a PhD? So usually a PhD takes like 4 years or even more. Uh, we usually get very low pay, and throughout the whole process, we feel a very high pressure. And also, we are dealing with difficult projects with considerable failure rate. That means most of the time we fail. Okay, so that's a common thing. So some students ask me like how I can be, how I can do this successfully. But I think one of the important mindset is that usually we fail because most of the research projects, they are research projects because they are difficult. So after going through all these hurdles, then what do we get in return, right? We spend a huge resources on this PhD degree, and we'll definitely get some research papers, hopefully. And maybe we can get sometimes free graduation attire. And of course, we might get a diploma, right? So that could potentially translate to maybe a few $100 more salary if you want to go to the industry. And so we have to ask ourselves, are those things the things we really want to get from this program, right? So since pursuing PhD is such a high stack investment, we will need to invest lots of the time and effort, and also it might hurt your mental healthness throughout the process. So instead of thinking about what we will get, I think we want to think more about like what we should get, right, throughout this whole process. So one of the most important things is that we can think of this whole PhD as a training program, just like whatever program you can get at the gyms, right? You can enroll a yoga course at the gyms, or you can go to do some weightlifting. So PhD is no different, right? In a PhD program, the most obvious skill that we will learn is, of course, the research techniques. But in addition to these research techniques, there are also some other important skills that we want to learn along the way. So for example, the writing and presentation skills, and the project management skills, and the ability to choose a research topic or develop a vision for the future research. So within those skills, in my opinion, I think the first skill, the being able to proficiently perform research techniques, is a master level. That means anyone who graduated with a master degree, they should be able to do that. And being able to choose the right topic and build a convincing vision, that is what we want to achieve at PhD level. Now, of course, we need to cultivate our presentation and management skills. These skills are often underaddressed and overlooked, but they are by no means the least important thing. In fact, they are also very critical, and they are very critical for the success of one's research career. So let's start the talk with something we are all familiar with, right? The research technique part. So in the first part of my talk, I will talk about some techniques we can use to do research. So it's literally like how to do research. For example, we can do minimum viable example. We can do from solvability to performance, and also another skill, which I'll call it the specialization and generalization. So what do I mean by them? So a minimum viable example means that we want to have an example. When we do the research, we want to have an example with just enough size to demonstrate some desired feature of the study. So what's the benefit of having such a MVE, the minimum viable example? The good thing about MVE is that with MVE, we can hand calculate some things and then verify those, verify and trace the whole derivation when we try to deal with our research subject. And more importantly, because this MVE is small, so we can determine if an idea could potentially work before we spend lots of effort on this subject. And in the end, we get nothing, right? So let's see an example of MVE. So an example here is that suppose we have a conjecture here, right? When going through a network, going through fewer links does not necessarily imply shorter traveling time. So this seems to be true, right? So then, in fact, it's a conjecture for a moment. Suppose we want to do research on this particular conjecture. Then the idea is that maybe this thing can be true because there are some links that are longer and there are some links that are shorter. So if we go through more links, but those links are shorter, then it's probably better than going fewer links, although those links are much longer. For example, in the current figure, we can see here, it's definitely an example showing that going through fewer links will result in might not result in shorter traveling time. Here, the numbers mean the time needed to go through each of the links. So from the very left to the very right, we want to go from the source S to the destination D. If we go from the top path, which consists of 3 links, each of them take time 1 to go through, then we can go from S to D in 3 units of time. But on the contrary, if we go through the bottom path, which consists of 2 links, each of them is 2 unit time to go through, then it takes 4 unit time to go through the whole network from S to D. So indeed, this is an example showing that this conjecture is true. Right? So it gives us some intuition that, okay, this conjecture is valid to some extent. But is that a minimum viable example? So the problem is that this is not a minimum viable example in that it's not the minimal scale we can get out of these examples. For example, we can have another much simpler network with only 3 links. So the shortest path will have 1 link at the bottom, which takes 3 unit time to go through, and the top path has 2 links. Each of them takes 1 unit time to go through. This is the right minimum viable example. So why do we care about the scale of those minimum viable examples? That the more links we have in the example, it will result in a much more complicated setting. So right now it seems so obvious that, oh, these 2 examples, each of them has no more than 5 links. So it doesn't matter that much. But sometimes we'll create much more complicated example, and we didn't know that we can actually further simplify this. So if we see some example, if we want to derive a minimum viable example, we probably want to ask ourselves, is this the simplest we can get? Can we further simplify it? So this is one of the research technique we can use to do research. Another technique I usually use is called from solvability to performance. So when we face a new research topic, we might have lots of the options there. We can derive whatever result, right? So it might feel lost for some people. Like, where should I start it? So here's what I suggest. Usually we want to start with whether this problem is solvable, right? And then you might ask, what does that mean by solvable? Right? Solvable means we can solve within a certain amount of resources given. Right? If we have infinite resources, or even suppose we have an oracle that will tell us all the answers. Of course, everything is solvable, but it's impractical. So most likely we have limited resources to address some problem. And within that amount of resources, we can ask whether the problem is solvable or not. And if it's solvable, then the problem becomes how can we derive a optimal or a good policy? And then how can we trade off those resources? If we spend more resources, can we get better results? And can we maybe instead using fewer resources, but then we might not get a result as good as we can get optimally, but then can we get something sufficiently optimal? So those are the questions we can ask if a problem is solvable. But instead, suppose the problem is not solvable, then we need to prove whether it's not solvable, why it is not solvable. Right? We cannot just say, hey, it's not solvable, and then we put it in our paper. Then a reviewer will question us like, is it not solvable because you don't know how to solve it, or is it really nobody can solve it if somebody else will come into this area and then try to solve this problem? So we need to attach a proof for it. And then once we have a proof that such a problem is not solvable, then we can ask whether the problem can be sufficiently approximable. That means, can we approximate the problem to a certain extent with reasonable resources? And of course, we have two possible outcomes. One is, yes, it's approximable. Then we want to have an algorithm that we can approximate the problem, right? So then we want to derive an approximation algorithm, means that the algorithm has performance guarantee, which is the approximation ratio. Or if we don't have such an approximation algorithm, then we need to show that it's not possible to approximate the problem. Yes, there are some problems that are very difficult, so it's not even possible for one to approximate it within a reasonable amount of time, right? Then we can feel more justified to propose some good heuristics to approach the problem. So through this whole this tree diagram, this provides us some sort of the trajectories we can choose to do a research. So when we get a problem, we can think about solvability first, and then we can think about the performance. So let's see an example. This is a classical example in computer science, which is the nest set problem. So nest set problem says that suppose we have a nest set with a fixed size, and then we have a set of goods with different sizes and values. We want to choose a certain subset of the goods that fits in the nest set, while we want to maximize the value we bring with that nest set. So it turns out this nest set problem wants us to choose some items, right? And then maybe we can choose those items with the highest aggregated value. And we can ask the first question through our tree diagram. Firstly, is this solvable, right? Is this problem solvable? So we might say, yes, it's solvable. How can we solve it? The most naive way we can solve it is that we can try every single possible subset, right? That will enumerate all possible outcomes, and then we just choose the one with the highest value. But it's not a good answer to this problem, because it turns out enumerating all possible outcomes from the set of the goods we have is very hard. Especially, it's very expensive, either numerically or computationally. So maybe our answer will be no, it's unlikely to solve it within a reasonable amount of time. We can definitely enumerate all possible outcomes, but it will take much longer time, which we cannot afford. So we might answer this question like, oh, it's not possible to solve it because it's unlikely we can solve it in a reasonable amount of time. So in computer science, we have a result called NP-hard. It's exactly saying something like that. It's unlikely that we can solve it in polynomial time of the problem size. So this is one way we can say, oh, it's not possible to solve because of the time constraint. Right? We cannot let the program run forever. If we could, of course, this problem is solvable to that scenario, but then not to this particular scenario. So our next question becomes, is it possible for us to approximate it, right? So one possible way we can do that is that we can propose some heuristics. For example, we can keep picking the item with the highest value. I think that's the most naive way we can solve this problem. We can try to figure out which item is the most valuable, and then we put it into our next step. And then we ask, oh, if we still have some room, let's pick up another item with the highest value. That's a good heuristic, but we cannot provide an approximation ratio for it, meaning that we cannot guarantee the performance. What if we have some item that is, for example, value 2, but it will occupy the whole net set, while we also have some other items that with value 1, and they are very tiny. So we probably want to take the sort of the value density into account in this case. So it turns out it's possible for us to approximate this net set problem using by picking the items with the highest value density first. And it is a 2 approximation algorithm. So in this example, we can see that although we have a new problem, which is a net set problem, we can use this tree diagram to guide us to solve this problem. First, we ask whether it is solvable, and then we ask whether it is approximable. Okay. Oh, by the way, if you have any question, you can just interrupt it. We do have some time to answer the questions. And then the next skill or the next technique I would like to introduce is the specialization and the generalization. So when we see a research topic, and sometimes we might not figure out a very good way to solve this problem like right away. It's very common. So what we can do is that we can specialize it. So instead of solving that hard version of the problem, can we simplify it to a simpler version, which allows us to maybe use a easier MVE to investigate or analyze that problem. So it's a specialization. We shrink the problem definition domain. And then we want to get some results from the for the shrunk domain that will guide us or provide us some intuition to solve the original problem. And once we have some solution to some problem, we could consider generalization. So we can generalize the problem setting to a wider range of problem domain, so that we can enlarge the problem definition, so that we can cover much wider class of problems that our method may apply. So let's see an example. So for example, I want to find a 2D path for a robot car. So this is also a classical control problem that suppose I have a map and I have a robot car. Can I find a path for the car to go through the whole map, right? From some point to another point, like Google Map, this kind of thing. Suppose we are given such a problem. And at the first glance, we might not have any idea like how we can solve this problem. So we could consider specialization. So that we can shrink the problem definition to a simpler graph. For example, we can say a simpler setting with only tree-like map. So tree means that we have a root and it basically goes through every single node with unique path. In that case, we can try to solve this problem in a simpler setting. So that will be finding the best path within a tree, right? That's one. And once we know how to solve this problem for finding 2D path for a robot car, maybe we can generalize it from 2-dimensional system to 3-dimensional system. For example, can we find a drone, we find a 3D path for it, and maybe we also want to avoid collision, or we can add more features like suppose we have mountains, we also have the geology constraints, something like that. So that will allow us to generalize a specific technique to a wider setting. So far we have talked about some techniques we can apply in our research. And those are some techniques you can try to use, and hopefully it will help you to do your research better. Is there any question? Okay, so the next thing I would like to talk about is something that's much more important, I think. Lots of time, I think people know how to do research. Actually, I believe in you that most of you guys here, you guys are the experts in doing research. So it's not a problem for you to generate some impressive research outcome. But the problem is that most likely we feel like the whole job is done by the time we generate those important or interesting research outcome. But it's not true. So once we have the research outcome, actually we need to present them. So only through presentation, we'll be able to let others to appreciate whatever results we derive. And that's how we can make our research more impactful. Oh, my meeting will end in 10 minutes. Okay. So the meeting will end in 10 minutes anyway. So I'll probably need to pause the meeting, and maybe you guys can re-enter if the meeting ends.
Yeah, I think Caltech ended like the premium Zoom account for all Caltech accounts. So.
Oh, really? Okay. Okay, yeah. That's fine. So sorry for that, but you can join after the meeting ends. So let's go through it. So firstly, I think writing and presentation is very important, and we'll talk about a few things here. First is the 3 key points of PSI, and we'll talk about what PSI means, and then logic flow and visual aid, and the conservation law of writing and reading. So there are 3 key points, the PSI, that we need to pay attention to when we try to present or try to write something. The first thing is that what is the problem, right? What is the problem that we want to address? What is our goal in doing this research? And then the next question we want to ask is, what's the special point that what we have done to approach such a problem? Okay. And then why our research is important, right? Why is our thing important that other people would like to learn? And what is good about our research? So when we try to write something, like we need to keep those PSI in our mind. So let's see an example to see how PSI works in a practical abstract. So here is an abstract I copied from one of my paper. We talk about, we have witnesses some emergence of several controlled parameterizations, and there are some parameterizations. And meanwhile, under some synthesis method, there are multiple realizations to adopt. And different synthesis methods have different target different scenarios, except for some case-by-case studies, we don't currently have a unified framework to understand the relationships. So to address this issue, we show that existing controlled synthesis method and realization proposal are all special cases of some simple lemma. And this simple lemma is good to for some scenarios. So we can try to identify these PSI points from, say, this paragraph. So firstly, we want to identify what's the problem. So the problem here is that except for some case-by-case studies, we don't currently have a unified framework to understand the relationship among some parameterizations. And then what's the special point that this research is giving is that we have some new lemma called realization stability lemma. And why this lemma is good? Because the lemma leads to easier equivalence proofs among existing methods and these kind of things. So that's why this lemma is good. So we justify this special point through this importance paragraph. And this applies to some other things too. I mean, in general, PSI points need not to be shown in this serial order. For example, in this particular paragraph, this is from one of John's paper. It talks about some state space formulas for H infinity problem, and then they derive some equations, and they also provide some linear fractional transformation of T. So in this paragraph, what are the PSI points? So firstly, what's the problem? The problem is that this paper is addressing such a problem, that the standard H infinity problem. How can we solve this standard H infinity problem? And then the special point for this paper is that it provides a state space formulas that derives all the controllers. So we can see here is that the PSI points are not ordered forward sequential order, right? It's actually ordered reversely. And then what's the good thing about this? What's the important thing about this is that this thing is simple, right? It's simple state space formulas. So that's why we need to pay attention to it. So through the analysis of PSI principle, we can see how how to learn some important concept, or how can we can write a concept to convey the importance to others. And then the following thing I want to talk about writing is about the logic flow. So we want to take care of the logic flow and that will greatly affect our writing. Let's look at the following paragraph. So we are considering the formulation of an uncertain convex program, which comes from the lack of the ability to specify constraints precisely, and hence uncertain parameter set is introduced. And as a result, the constraint enforcement philosophy plays an important role in obtaining a solution to UCP, and there are two main approaches commonly used to solve UCP: the robust optimization paradigm and chains constraint paradigm. In this paper, we adopt a sampling technique to solve UCP with chains constraints. So this is a typical paragraph we might see from some papers. Okay? But what's the problem of this is that we mix lots of the ideas into a paragraph that makes it hard to read. Okay? So you might or might not agree with me, but then let's see the example. So if we reorganize this paragraph in the following, we say the UCP embeds a constraint precision in its uncertain parameter set. So this is an idea, right? This UCP embeds a constraint in precision in its parameter set. And then we talk about the two approaches that we can use to solve UCP, the robust approach and the chains constraint approach. And then the third paragraph, we talk about, in this paper, we use whatever technique to solve UCP. So if I'm an impatient reader, I only read a few sentences from each of the paragraph, then I will understand that, okay, this paper is talking about UCP. It can be solved by two possible methods. And then this method is the method introduced in this paper is the sampling technique. But in contrast, if we see the previous paragraph, then if we only read one of the sentences in the paragraph, then we might not lead to the same conclusion. So it's better to introduce one idea at a time instead of mix lots of the ideas within a paragraph. The logic flow is very important, and also we want to order the paragraphs by its importance. So previously we talked about this, talk about one idea per paragraph, and that also applies to how we also order those ideas. So we introduce one idea per paragraph, but then how can we present those ideas? I suggest that we should present the ideas by its importance, and for the following reason. So most likely people, if you get a paper and you start reading the paper, and you are a very impatient reader, then you only read few sentences per paragraph. And as a writer, you never know when the reader will give up reading. So you want to make sure the most important thing is put at the front, right? So let's see the following example. This is an example from another paper. That R be the realization matrix and S be the internal stability matrix. And we have some state dynamics. And we have this R equal to this, and by some lemma, so we have such a result that Zi minus A minus B times this Sx Ux equal to I. Okay. So what's the problem or what's the issue in this paragraph is that we need to go through multiple lines to get to our main results. So what can we do to improve this paragraph by reordering the paragraphs or sentences by its importance? So we can do something like this. For a system with such a system dynamics, we have this result. Actually, this is the state feedback SOS. I think the people in John's group may know very well already. And then we can prove such a result by the realization stability lemma, which we could include a proof after this paragraph, or maybe we can omit it. We can send it to the appendix, and we have already presented our main result. So we don't really need to include lots of things to burden the reader before they can learn the most important thing. So what we want to do is usually, trigger their interest by the most important result, and then provide them the additional information they need to know if they want to dig further. And the third thing about logic flow is that we want to clarify the narrative among ideas. Okay. So here is something I also often see in lots of papers. We have, for example, in the following paragraph, we have x be our important vector, and we have some theorems which says u equal to kx, and y equal to g of u, and equal to g of kx. And then that's it. Okay. Some people present the result like that. But I would say it's probably not a good idea to present in this way, because as a reader, as a writer, we know the narrative, or we know the reasons why we need those results. But as a reader, you probably have no idea, or at least I don't have any idea, like why we want those results. So instead of just putting the results in a list of points, we want to give the readers more hints on how to read this whole paragraph. For example, we can say, let x be our important vector, and we show in the following theorem 1 that another important vector u can be derived from x through some linear map k. So in this way, we emphasize the importance of that linear map k. Right? And then we can say, and we can introduce our theorem 1, and then how can we connect the results between theorem 1 and theorem 2? We probably also need another narrative in between. We can say theorem 1 allows us to express u in terms of x, and therefore we can compute our desired measurement y using x via the following theorem. So in this way, the reader will have much more clear idea what we are doing through this, why we need these two theorems here. So I think that's also very important, because sometimes we forget about the narrative behind the scene. We feel, oh, we have the most important results, so we just present it in the paper, but it's not enough for the reader. Okay. And another thing I want to talk about is the visual aid. So I think lots of people, especially the, oh, what's going on? Oh, yes. So especially the advisors, they might have told you the importance of the visual aid, right? They will say, hey, put some figures in your paper. But how can we put the figures in the paper? Right? So let's see the example. So sometimes we see this example that we have a figure, we have some colors, right? We have some algorithms. We compare our algorithm with the optimum. And great, this is and we have the caption saying that this is the normalized update time. So what's the problem of this figure is that if you think about a researcher, usually they might read a paper in a color format, but lots of other researchers, they will print out the paper to read. Right? If they print the paper out, then this figure will become all black and white, and they will wonder, what do you mean there? What does that mean by optimum? What does that mean by our algorithm? And what does that mean by other? Because from a black and white paper, we cannot see anything different among those lines. Therefore, we need different textures for different lines. Okay? So that's better for black and white printing. And there's another problem in this figure is that the caption provides no information. So caption is there for some reason. Right? If we only say this figure is about normalized update time, the reader has already known that through the y-axis label. So this caption provides no information. We should either remove it or we should enhance it with more information. In fact, we should probably enhance it with more information as follows. Like we can say our algorithm performs close to the optimum, and it achieves the optimum for about 80% of the test cases. Also, its update time is 2 to 3 times shorter than the other algorithm. So we can see that in this version, the caption provides much more information, and it's also much more invaluable information because it guides the reader to read or to sort of pass through this figure, right? Instead of just saying, oh, there is a figure here. And this is also important because lots of the people read the paper not from the context, but from the figures. So that's why the caption in the figure should serve a much more important role between the writer and the reader, right? So we should convey more information to help the reader to parse the figure instead of just saying, hey, there is a figure there. And the final thing I want to introduce about writing a presentation is a mindset. It's the conservation law of writing and reading. So this is something I learned from another professor when I was in Cornell. He said, the effort spent on writing plus the effort spent on reading is a constant. So what does that mean? That means if we spend less time in writing or spend less effort, not necessarily time, less effort in writing, then the reader needs to spend much more effort on writing, on reading, so that they can understand what we're talking about. And that's not good because people have limited attention. They might not want to spend time to read the paper if it's too troublesome for them to read. So we need to know how easy can one distinguish, can one read this thing. And that also has something to do with knowing your audience, right? You need to know the average audience that you are presenting to, so you can determine what is the reasonable amount of information you need to convey in the paper so that the reader will feel comfortable reading our contributions, right? So that's also a very important mindset. Okay, so after the writing and the presentation, we also have a very important critical topic we want to talk about, which is the project management. So most of the time we can figure out a very bright idea. We can also write great papers, but if we cannot deliver that in time, then nothing matters, right? We cannot submit the paper because we cannot deliver it. And the project management is very important. I especially want to talk about two things. One is the plan before work, and the other is the work-life balance. So here's a typical example of a project, right? Suppose we are 10 days away from some deadline. So here, say from today to October 23rd, we have 10 days. So we feel great, we have 10 days, we can work on our project, and I'll definitely be able to do a masterpiece. But is that really the case? Let's re-examine our schedule a bit. We definitely need some time to sleep, say from the 0 to 8, we need to sleep. And then we also need some time to eat something, right? That's definitely the case. Suppose we only eat 2 meals per day, the lunch and the dinner. Then each of them take out 1 hour, which is very quick already. And we also need some time to do other things. For example, we need to wash our clothes, we need to do some grocery shopping, we need to do other things, right? So suppose we don't work during the weekend. And we are also taking some courses, right? As a grad student, you might have 2 courses. So it will take out some time from your schedule. And we also need some meetings, right? We will probably also meet someone, meet your advisor, meet your collaborators. So you also have some time spent on meeting. And maybe you also want to hang out with some friends. And I think it's reasonable to hang out with friends once per week. Or maybe you will do much more because you want to talk about some things with your friends, right? So after we eliminate those times that we are actually occupied, though it seems like we have 10 days to spend, in fact, we only get 63 hours. So we don't really have 10 days. In fact, we have less than 3 days to spend to finish the project. So time is actually much tighter than we think if we don't think carefully beforehand. Okay, so that's why we need to we need to master another skill called project management, and then we also need to do something called backward planning. Let's see how we usually do our research. We start with some idea, and then we work very hard to figure out some interesting results. And perhaps we also need to do some experiments to demonstrate the benefit of our research or our results. And then we finally start writing our manuscript, and boom, we have our research, and it's a paper, and we're all happy about it. But what's the what's the issue in this approach, right? One issue of this open loop approach is that it is hard to control the finishing time. Say we start on October 14th. When will we get the paper? If we just blindly do that open loop, then it's very hard for us to control when we are going to finish the project. Therefore, I would suggest to do a backward planning. We first decide a deadline before which the paper should be fully written, for example, 10 days later. Then we can go backward in each step. We can say, oh, if we want to get the paper on October 23rd, then for instance, we need to finish our paper by, we need to finish writing or at least start writing on October 20th, right? And because of that, if we need to write, we need to have the results. So we can also plan the other previous action items accordingly. For example, we need to finish coding on October 19th, and we need to because we need to finish coding, we need the theory, so we need to finish our theory development by October 17th. In this way, we have a clear timeline on what we should do. Right? That will lead to some timeline like this. But then you might ask, how do we know how long each task takes? And that will have something to do with knowing yourself, right? You have to know yourself in order to determine how long each task takes you. And then it's also very important for us to identify the dependencies carefully. For example, if we need to do the experiment, we need to have the result first so we can do the experiment. That means the experiment must be happening after the development of our theory. So that will constrain our schedule, because sometimes we feel like, oh, we developed the theory before the deadline of the paper, and if we crank out, we can definitely write the paper in one day. But that's not true, because we still need to do simulations, which take up to 2 days to run. Then we are actually doomed if we just finish the theory 1 day before the deadline. Right? So those things we'll have to take into account. And as we all do theory, we know, or all do any kind of research, we always know that research is not as planned, right? Most of the time we have unexpected things happen. Like we develop a theory, we feel like this theory will work, but it turns out it doesn't work. So that's why when we arrange our tests, actually we need to leave some buffer time beforehand. So we because of those unexpected things, we can use the buffer time to absorb those uncertainties. And because we also need to leave this buffer time, that means we also need to squeeze each task a bit in our schedule. So if we look our schedule in this perspective, we know that 10 days or this kind of thing is actually pretty short. So that's very critical for us to, that's why it's very critical for us to plan ahead. Plan ahead, although it's 2 months or 3 months away, it might not be, it might not give you enough time to finish because how complicated the task is. And another important thing about project management is the work-life balance. Here's a sentence from my PhD advisor. He says, PhD is a marathon instead of a 100-meter dash. We need to maintain a sustainable pace to stay in the race. Okay, so sometimes we want to cram out a bit so we can meet the deadline, but we need to know it's not sustainable. In fact, every single day, we only have certain amount of mental power and certain amount of physical power. So we wouldn't be able to spend more time. For example, if you only have 3 hours mental power, then it's not possible for us to keep working on some intense theory derivation for more than 3 hours. And for that, that's why we need to plan very carefully. We need to do long-term plans rather than always rush through the deadline at the last minute. Okay. And the last part of this talk, I want to talk about the PhD level thing, which is how can we get ideas, right? How can we get a vision? How can we establish our vision? How can we get a good idea? And then it has something to do with the topic selection and also the vision development. So how can we select our topic? As Jessin just pointed out, we previously had the PSI principle, right? The PSI questions. We can use the PSI question to ask whether an idea is a good idea, right? What is this problem? And what's the goal? What's the special point? Why we will do in this research project? And even if we have done that, would that be an important outcome? We have to ask ourselves that. And sometimes we also need to ask whether it's possible to finish a project. We want to form some preliminary intuition. If we don't even know how we can finish a project, then it's probably beyond our control, right? And then the uncertainty is too large for us to control. And after we determine a possible direction, we can use the minimum viable example that we introduced previously to check if the topic is doable and if the result matches the preliminary intuition. And then we can specialize the MVE, or we can use whatever technique we introduced previously, like the solvability to performance tree diagram to solve this MVE. And once we solve the MVE, we can generalize this MVE and to a larger set of problems, and we can pay attention to those results that are different from our intuition. Maybe through this generalization, for example, from 2D to 3D, we suddenly realize there are some other factors that will affect our results. And maybe that's also an inspiring point. Though that's also where the fund of research comes from. And lastly, I want to talk about the vision. So vision is pretty much an art. So, but how can we do an art is usually through practicing, right? If you have painted something and you still need to acquire the basic skills in order to paint a masterpiece. So the same thing for research. If we want to build a reasonable vision, we need to know the history. That means we need to do extensive literature review. We need to ask ourselves through every single paper we read, using the PSI principle. We ask what's the problem they are solving and why their results are important. That will help us to build a system or to understand why people do the problem in this particular manner in the history, right? And then that will also help us to understand how we can do differently in the future. Then once we sort of get some idea of what people have done in the past, we can ask a few questions. Then what do people need at the moment, right? And why do we need that? For example, before iPhone, people feel like, oh, we need a cell phone, and also we need the camera. But then iPhone says, maybe people want to take photo everywhere, so I want to combine the camera with something you will bring every day, like the phone. So it's something people need, right? So and why do we need it? Because we need to take photos from time to time. So that justifies this need. And then what kind of future we can propose is that we propose a future of camera embedded phones, right? Or maybe with the touch screen based phones, something like that. So through this way, we can justify whether our vision makes sense. And sometimes you also need to listen to others to learn what other people think about the future. How do they justify whether some vision will work? So what usually it has something to do with why something matters. Okay. So we have talked about some different things. Let me revisit them. One is, of course, we need some skills to do the research, and we need some presentation and writing skills. We need some project management skills, and also some ideas. And here is what I think about research. So whether a research is impactful or a research is important, is usually can be written down in the following formula, which is the project management skill times the 50% of your idea and maybe 30% of your presenting skills and 20% of your research skill. That being said, the idea is probably the most important in the research, but something even more important is your project management skill. If you cannot deliver anything, then whatever good idea or your research doesn't matter. And once you have your idea, you need to present it well so other people will appreciate the idea that we present. So that's why, although we might be able to master the research skills, we also still have lots of other things we need to master in order for our research to be impactful. Okay. So finally, I have said lots of things in this talk, but nothing I said really matters unless it suits your style. And only you will know which style suits you the best. So you have to build your own judgment and taste. Don't fully take whatever I said for granted. So you can also build your own philosophy. In the end, you guys are all PhD. So you guys are going to have your own philosophies. And I'm glad to be able to work with you here at Caltech. And I would especially like to thank my collaborators. And many ideas in this talk are learned from my interaction with my collaborators. And if you're interested in contacting me, here's my website and my soon to expire email. But I will update my contact information on my website. So as a Taiwanese, I would like to conclude the talk with the following Taiwanese idiom. Hi ben ka kia gu lang e, which means the stage belongs to those who persevere. So I wish you all the best in your future career and research.